Right now, a rover the size of a car is drilling into the floor of an ancient Martian lake, collecting rock samples that may contain the chemical signatures of life that existed 3 billion years ago. At the same time, the world's most powerful privately funded rocket is being tested specifically to carry human beings to that same planet within this decade. Engineers at space agencies across 3 continents are designing habitats, life support systems, and radiation shields for a world they have never visited. And in boardrooms, universities, and government offices, serious people with serious credentials are debating not whether humans will go to Mars, but when, how many, and whether they will ever come back. Mars is no longer a dream, it is a plan. The question is whether the planet that killed its own oceans 3 billion years ago can become a second home for the species that is rapidly exhausting its first one. Welcome to Space Review. If this is your first time here, we go deep on the biggest questions in space science every single week. Subscribe, hit the bell, and stay with us, because this story covers everything from ancient Martian oceans to the engineering of underground cities, and every section changes what you thought you knew about the red planet. Mars has captured the human imagination for centuries. Long before telescopes, ancient civilizations tracked its blood-red glow across the night sky and built mythologies around it. In the 20th century, science fiction writers populated it with civilizations, canals, and wars. Then the first spacecraft arrived, and the romantic version died. No canals, no cities, no visible life, just a cold, barren, rust-colored desert with an atmosphere so thin it barely registers, radiation levels that would be lethal over long exposures, and temperatures that average -60 degrees Celsius. And yet, the more we have studied Mars, the more the case for going there has grown stronger, not weaker. Because beneath that hostile surface lies a story far more complex than the dead world early missions suggested. Mars was once warm. It was once wet. It once had a magnetic field, a thick atmosphere, and possibly the conditions for life. Something catastrophic took all of that away. Understanding what happened to Mars is not just a scientific puzzle. It is a warning, and possibly a roadmap, for what humanity might one day need to do to survive. 4 billion years ago, Mars was a different world entirely. The evidence is written into its geology in ways that no serious scientist disputes. Ancient river valleys, carved by flowing water, stretch for thousands of kilometers across the Martian surface. Massive delta formations, identical in structure to river deltas on Earth, sit at the edges of what were once lake basins. Minerals like clay and sulfate, which only form in the presence of liquid water, are found across wide regions of the planet. And the Curiosity and Perseverance rovers have both directly confirmed that the areas they are exploring were once the floors of ancient lakes that held water for potentially millions of years. Mars was not just briefly wet. It appears to have had a sustained hydrological cycle, rain, rivers, lakes, and possibly oceans, for hundreds of millions of years during what geologists call the Noachian period. The northern lowlands of Mars, a vast depression covering about a third of the planet's surface, may have held a shallow ocean containing more water than the Arctic Ocean on Earth today. The shoreline features of that ancient ocean, terraced formations and erosion patterns consistent with standing water, have been mapped from orbit. So what happened? The leading explanation involves the loss of Mars's magnetic field. Unlike Earth, Mars does not have a global magnetic field today. Scientists believe it once did, generated by a molten iron core similar to Earth's. But Mars is smaller than Earth, and its core cooled and solidified faster. When the magnetic field collapsed, the solar wind began stripping the Martian atmosphere away, molecule by molecule, over hundreds of millions of years. Without a thick atmosphere, liquid water could no longer exist on the surface. Temperatures dropped, the water froze, evaporated into space, or retreated underground. and Mars became the desert we see today. This is the Martian tragedy, a planet that may have had everything necessary for life, that may have actually produced life, undone by its own size, too small to hold its heat, too small to keep its shield. And the reason this matters for humanity's future is that we are not going to Mars to find what was there. We are going because of what we might be able to rebuild. Before examining how humans might live on Mars, it is worth asking the prior question. Why Mars at all? The solar system has other destinations. Why not the Moon, or Venus, or one of the moons of Jupiter? The Moon is the obvious first answer, and it is indeed where NASA's Artemis program is focused for the near term. The Moon is close, roughly 3 days away, which makes resupply and emergency return feasible in ways that nothing further can match. But the Moon has serious limitations as a permanent home. It has no atmosphere, no magnetic field, and a day-night cycle of 29 Earth days that creates extreme temperature swings between blistering heat and deep cold. It has water ice at the poles, but very limited other resources. The Moon may become an important way station and a site for scientific research, but most serious long-term settlement proposals treat it as a stepping stone rather than a destination. Venus is Earth's twin in size, but a nightmare in every other respect. Surface temperatures of 465 degrees Celsius, atmospheric pressure 90 times that of Earth, clouds of sulfuric acid. Any surface infrastructure would be destroyed rapidly. Some researchers have proposed floating settlements in the upper atmosphere of Venus, where temperatures and pressures are more Earth-like, but this remains far more speculative and far more technically challenging than Mars. The moons of Jupiter and Saturn, particularly Europa and Enceladus, are enormously interesting from a scientific standpoint, but they are vastly farther away and sit deep inside radiation belts generated by their host planets that would make long-term human habitation extraordinarily difficult. Mars, by comparison, offers a combination of advantages that no other destination in the solar system matches. It has a day almost identical in length to Earth's, 24 hours and 37 minutes. It has a thin but real atmosphere, mostly carbon dioxide, which provides some protection and serves as a raw material for fuel and oxygen production. It has confirmed water ice at both poles and suspected subsurface ice across large regions of the planet. It has enough gravity, about 38% of Earth's, to be meaningful for long-term human physiology in ways that the near-zero gravity of space or the Moon cannot replicate. It has a surface area approximately equal to all the land on Earth, and it is close enough that, at the right orbital alignment, a spacecraft can reach it in as little as 6 to 9 months. No other destination combines all of these factors. Mars is not perfect, but it is the least imperfect option available, and the gap between Mars and everything else is significant. Understanding why Mars is the target is straightforward. Understanding what it will actually take to get humans there and keep them alive requires confronting a set of challenges that are genuinely daunting, and being honest about which ones are close to solved and which ones remain wide open. The first and most immediate challenge is the journey itself. At the right orbital alignment, which occurs roughly every 26 months, Mars is between 55 and 400 million kilometers from Earth, depending on where both planets are in their orbits. A transit using current propulsion technology takes between 6 and 9 months. 6 to 9 months in microgravity causes serious physiological damage. Bone density drops, muscle mass declines. Vision can be affected by fluid shifts in the skull that alter pressure on the optic nerve. Cardiovascular fitness deteriorates. The human body is not designed for extended weightlessness, and the cumulative effects of a long transit are a real medical concern that no mission can simply ignore. Radiation is arguably the most serious unsolved problem. In deep space, beyond Earth's protective magnetic field, Astronauts are exposed to galactic cosmic rays and periodic blasts of solar energetic particles from solar flares. The radiation dose accumulated during a round trip to Mars, plus time on the surface, could exceed the lifetime limits currently set by NASA by a significant margin. The Martian surface itself offers some protection, since the planet has a thin atmosphere and terrain that can block radiation from below, and habitats buried under meters of Martian soil would substantially reduce exposure. But the transit is unavoidable, and shielding a spacecraft adequately against cosmic rays without adding prohibitive mass is an engineering problem that does not yet have a fully satisfactory solution. The atmosphere of Mars, while real, is approximately 1% as dense as Earth's. It is composed primarily of carbon dioxide with small amounts of nitrogen, argon, and trace gases. It provides almost no breathable oxygen and almost no atmospheric pressure. Humans require pressurized habitats at all times on the surface, and any system failure that exposes a habitat to the Martian atmosphere is immediately life-threatening. Every component of a Mars habitat, every seal, every valve, every pressure vessel, must function without failure for years or decades, far from any possibility of replacement or rescue. Food production on Mars cannot rely indefinitely on resupply from Earth. The communication delay between Earth and Mars ranges from 3 to 22 minutes, depending on orbital positions, meaning a real-time conversation is impossible, and any emergency must be handled independently by the crew on the ground. A Mars settlement must eventually become self-sufficient, growing its own food, recycling its own water, generating its own power, and manufacturing its own replacement parts. The technologies to do all of this exist in prototype or early operational form, but scaling them to support a permanent human community is a challenge of enormous complexity. Here is something that reframes the entire challenge. Mars may already have some of what settlers will need, hidden just below the surface. The Charade and Marsis radar instruments aboard Mars orbiters have detected what appear to be substantial deposits of water ice buried beneath the Martian surface at depths accessible to near-future drilling technology. Some estimates suggest that if all the confirmed water ice on Mars were melted, it would cover the entire planet in a shallow ocean, roughly 35 meters deep. That water, if accessible, represents not just drinking water, but oxygen for breathing, when split into hydrogen and oxygen by electrolysis, and hydrogen for fuel production. NASA's MOXIE experiment, a small instrument aboard the Perseverance rover, has already demonstrated something remarkable. It successfully converted carbon dioxide from the Martian atmosphere into breathable oxygen using a process called solid oxide electrolysis. In 2023, it produced enough oxygen in 1 hour to sustain a small dog, and over its operational life, it demonstrated that the technology works reliably in Martian conditions. A scaled-up version of MOXIE could eventually produce oxygen for both breathing and rocket propellant, dramatically reducing what future missions need to carry from Earth. The Martian soil itself, called regolith, contains a range of minerals, including iron, magnesium, aluminum, and silicon. It could in principle be used to manufacture construction materials, ceramics, and glass. 3D printing with regolith has been tested in laboratory conditions on Earth, and several proposals for Martian Habitat Construction Center on robotic systems that would build structures from local materials before any humans arrive. And then, there is the most surprising potential resource of all: perchlorate. Martian soil contains significant concentrations of perchlorate salts, which are toxic to humans, but also highly energetic compounds that could potentially be used as rocket propellant or processed to extract oxygen. The same chemical that makes Martian soil dangerous to eat may turn out to be a resource rather than just a problem. Beyond the immediate challenge of keeping a small crew alive, some scientists and engineers are already thinking about a much longer timescale. Terraforming Mars The process of transforming its environment to make it more Earth-like on a planetary scale is the most ambitious idea in the history of space exploration. And while it remains far beyond current technology, it is no longer considered purely science fiction. The basic concept is straightforward. Mars needs a thicker atmosphere, higher temperatures, and eventually liquid water on its surface. To achieve this, large quantities of greenhouse gases would need to be introduced into the Martian atmosphere to trigger a warming cycle. Several mechanisms have been proposed. Factories producing powerful greenhouse gases, like perfluorocarbons, could be built on the surface. Asteroid redirects could deliver volatile-rich materials to the Martian surface. Orbital mirrors could focus additional sunlight onto the poles to sublimate the carbon dioxide ice caps and release gas into the atmosphere. Mining subsurface carbon dioxide deposits could accelerate the process. The timeline estimates for meaningful terraforming range from centuries to tens of thousands of years, depending on the method and the target conditions. Carl Sagan first seriously proposed the concept in a 1973 paper. More recent analyses suggest that even aggressive terraforming could not fully restore a breathable, unprotected atmosphere to Mars because the planet lacks a magnetic field to prevent the solar wind from stripping it away again. Some researchers propose generating an artificial magnetic field using a large superconducting ring around the planet, or by positioning a magnetic shield at the Mars-Sun L1 Lagrange point. These proposals are speculative, but not physically impossible. What most scientists agree on is that any serious terraforming effort would require not decades, but generations of sustained commitment, a civilization-level project that would need to begin long before it could be completed. The practical implication is that the first generations of Mars settlers would not be terraformers. They would be tunnel builders, habitat engineers, and farmers inside pressurized environments, laying the groundwork for a process that their descendants might eventually complete. The scientific case for Mars as a human destination has been substantially strengthened by a series of recent findings that paint an increasingly detailed picture of what the planet offers and what it demands. Perseverance has been operating in Jezero Crater, an ancient river delta, since February 2021. The samples it has collected from layered sedimentary rock deposited by ancient water over long periods are considered the most promising yet for potential biosignatures. The rover has sealed more than 20 sample tubes, which are waiting on the Martian surface for a future Mars sample return mission to retrieve them. Scientists at NASA and the European Space Agency have described the sample collection as the most scientifically valuable set of materials ever prepared for return to Earth. In 2022, data from the Mars InSight lander, which monitored Marsquakes from its landing in 2018 until it went silent in December 2022, when dust covered its solar panels, revealed that Mars has a surprisingly large liquid outer core, suggesting the planet retains more internal heat than previously thought. This has implications for subsurface geothermal energy, potentially a power source for future settlements, and for the possibility that some regions of the subsurface may still have conditions warm enough to support microbial life. China's Zhurong rover, which landed in May 2021, detected signs of liquid water activity, far more recent than expected, potentially within the last few 100,000 years, in a region of the northern plains. If confirmed, this would significantly update the timeline of Martian habitability and strengthen the case for subsurface liquid water existing somewhere on Mars today. SpaceX's Starship, the fully reusable heavy-lift vehicle being developed explicitly with Mars in mind, completed its first fully successful integrated flight test in 2024, demonstrating booster catch and full vehicle recovery for the first time. The architecture Elon Musk has outlined calls for a fleet of Starships to deliver cargo to Mars in advance of crewed missions, establishing propellant production on the surface using Martian resources before any humans arrive. Whether that timeline holds is debated, But the vehicle itself is real, and it is flying. If humanity successfully establishes a permanent presence on Mars, the implications extend far beyond the planet itself. A self-sustaining Mars colony would represent the first time in history that the human species existed on more than one world simultaneously. That is not just a milestone. It is a qualitative change in the nature of human civilization. From a purely survival standpoint, a second inhabited world dramatically reduces the existential risk facing humanity. A single catastrophic event, an asteroid impact, a runaway climate shift, a pandemic of unprecedented scale, a nuclear exchange, any of these could in theory end human civilization on Earth. A self-sufficient Mars colony would survive any of them. This is the argument that motivates much of the philosophical case for Mars settlement beyond the scientific one. It is not that Earth is going to end soon. It is that putting all of civilization on a single planet is, from a long-term risk management perspective, an extraordinary gamble. There is also the question of what a multi-planetary humanity would look like culturally, politically, and economically. A Mars colony separated from Earth by months of transit time and up to 22 minutes of communication delay would inevitably develop its own governance, its own culture, its own priorities. The history of terrestrial colonization is deeply complicated and often deeply troubling, and the lessons of that history are ones that serious Mars settlement advocates are beginning to engage with more directly, asking questions about who gets to go, who decides the rules, and who benefits from Martian resources. These are not questions with easy answers, but they are questions that will need answers before the first permanent settlers arrive, not after. Mars is not a comfortable destination. It is cold, irradiated, airless, and distant. Its soil contains toxic chemicals. Its atmosphere cannot be breathed. Its surface is bombarded by ultraviolet radiation, intense enough to sterilize exposed organic material. Everything about it is difficult, and nothing about getting there and staying there is close to routine. And yet the case for Mars has never been stronger. We know it was once warm and wet. We know it has water ice in enormous quantities. We know its atmosphere, thin as it is, provides raw materials for oxygen and fuel. We know its day length matches ours closely enough that our biology would recognize it. We know its geology is stable, and its resources, while challenging to extract, are real. We know the technology to get there is being built and tested right now, not in laboratories, but on launch pads. And we know that the scientific questions it holds about the history of life in the solar system, about what makes a planet fail, about what it takes for biology to begin, are among the most important questions our species has ever asked. The first humans to walk on Mars are probably alive today. They are training, or studying, or perhaps still children who have not yet decided what they want to be. The world they will walk on is ancient, scarred, and silent. But it is not dead, not yet fully understood, not yet finished with its surprises. And if we are careful, and patient, and honest about both the risks and the possibilities, it may one day be home. If this changed how you think about Mars, drop a comment below and tell us the single biggest challenge you think stands between humanity and a permanent Martian settlement. Is it radiation, the journey, food production, or something else entirely? Share this with someone who thinks Mars is just a distant red dot, because the reality is far more complicated and far more compelling than most people realize. Subscribe to Space Review, because next time we are tackling another question that sounds settled but absolutely is not, and it will take you somewhere you did not expect.